Welcome back. Mass spec on nitrogen-containing compounds. Let's take a look at a couple of them, amines and amides. We've been seeing carbonyls, alcohols, acids, and so on, and benzene compounds. Let's take a look at what nitrogen can do. One of the things about nitrogen-containing compounds is that if they have a single nitrogen or an odd number of nitrogens in the molecule, the molecular ion peak would be an odd number. For example, take ammonia. This nitrogen is 14 and then 3 hydrogens. That's going to be 17. And same here, you can see if you have one nitrogen, but if you have two nitrogens, I mean when you add two odd numbers together, then they'll become an even number. So therefore when you have even number of nitrogens, then you will see that your molecular ion peak again would become a even number. Let's do a simple molecule. This is just an amine, a primary amine. Let's see what are the possibilities for this molecule. So the molecular ion here is primary. It's got 2 hydrogens on it and a lone pair. And so you can have this being bombarded by the electron ionization that we talked about and kind of knock out one of these. So let's say you have that then going over to your molecular ion peak, and that is going to be your 73. The molecular ion peak here is very weak, but there are other peaks here that are very stable. So let's take a look at what's going on. As soon as this form is going to break up, and here 73 going to 72 is only a hydrogen. So over here, if you want a positive ion, you can see how this hydrogen is going to break up. So let's call this A. That hydrogen can then break up and go away as a radical and make a double bond right here. So you can see how that can give you a double bonded, like an iminium ion here. And you lost your lone pair from there to make the double bond. Therefore, you are going to then have a positive charge, because if you do the formal charge, nitrogen's group 5 minus 1, 2, 3, 4 in the box, that's going to be a +1. But that's going to hit your detector and give you a 72. So that would be the A. Well, what else can we do? Typically, when you have a functional group that's a heteroatom here, you can have alpha cleavage, and you can see there's an alpha cleavage that's possible between the ethyl and this group, or you can see that there's another possibility here of going on the other side and taking out an methyl. Let's examine all of those. So let's do B, and in our B scheme, you can have the same molecule here. So you're going to talk about the same nitrogen here that got impacted by the electron ionization. It's got a lone pair and a positive where the electron was taken off. Now this can form a double bond with this carbon bond. And so now you can see that if you form a double bond here to that nitrogen, you will have the 2 hydrogens there, and the formal charge, just like here, would be 5 minus 4. That's a 1. So this is now just taking 29 CH2, CH3. That's a radical here, and that's a 29. So you started up with a 73, and so that could be your 44. Let's look at what could happen if we did this on the other side, C. So let's look at C. Same thing, and you can see the positive going away. This hydrogen will be here. It's going to go with one of these to make a double bond there. This one goes away, and you can have a double bond here for that iminium ion, and that would have a formal charge of +1, and your methyl's gone away as a radical gets sucked out of the tube by a vacuum, while this gets accelerated with the electric field and the magnetic field towards the detector. So this is going to be 15, and so 73 take away 15 is going to be 58. We kind of accounted for most of our major peaks: 72, 44, and 58. Those are the major peaks. All the others are really tiny. There's one here, 18, and what do you think that could be? 18, it can't be a methyl or an ethyl. Even an ammonia is 17. So if you add one more hydrogen to that, you would get an ammonium ion. So with all of this, you can have some ammonium getting out, and that would be your 18. So that's just a very simple scheme. Let's see what happens when you get to a slightly larger molecule with a nitrogen. So here we have a benzamide pretty much, and benzamide has got a nitrogen here with 1 lone pair, oxygen here with 2 lone pairs, and so lots of lone pairs there to get, impinged by those high energy electrons coming from that filament going towards the anode. It hits the molecule, knocks off some of the electrons, and it could knock it off here or here. Let's see what would happen if we knock it off here. So knock off this electron, and you are going to get your molecular ion peak at 121. So here is your carbonyl, and this is at 121. Well, we are going from then traveling from 121 to 105, and what would that be? Let's see. This is going to be a 16. What? Minus 16. 16 is typically methane, but here there is no chance of having methane. This is 28. This is 77. What about this guy? That could be a possibility. Let's see if that would work out. Well, in order to do that, we got to get this guy out. And so we do the same thing all over again. We make a bond here between this and the oxygen, just like we did here with the nitrogen. So let's break up the sigma bond here. So this is going to go over here and make a pi bond with the oxygen. So you can see how that is going to give you a carbon with a triple bond. Now that is an sp because it's got triple bond. You lost that single electron, so you pretty much got rid of the whole lone pair one at a time here, and that's in here. And if you look at the formal charge here, there's going to be 1, 2, 3, 4, 5 in the box. So 6 minus 5 is going to be a +1, and we've seen this many times now. And the NH2 will go away as a radical. Nitrogen with 1, 2, 3, 4, 5. 5 minus 5 is a 0, so it's not going to record on the machine. It's going to go out. So this is going to be 105. 105 going to 77, what do you think that is? So 105 going to 77, that is going to be 28 units. We know what a 28 is. It can be ethylene, or it could be carbon monoxide. And that's what we have here. Well, let's say this is A, and we can go from, that's your A, and then we can go from this pathway, we call this B, and we can do a B pathway over here. and we can go from this 105. So the 105 here, these electrons both heterologically cleave to give you a phenyl cation. A benzyl would have another XCH2. This is just a phenyl. And we have a CO, carbon monoxide. So here, 1, 2, 3, 4, 5. So that's 28. So here's your carbon monoxide. Well, we typically write this as CO. Coming out and giving you a peak at 77. What about 51? That's kind of a strange number. And what about 44? Well, 16, this is 28. If you add this together, that's 44. So that's probably this whole molecule getting out. Let's look at how we can do that. I'm just going to write this as C. So here we can start with the initial molecule. So now I hope you got a good sense of how this works. Every single time it's pretty much the same story. You just break up fragments and then you add them up and you make sure that they match with the initial, and you kind of have a good idea of what a 15 is, ethyl, methyl, propyl, carbon monoxide, ammonium, things like that, common groups that can leave. Then you piece it all together. So here is your nitrogen, and let's say you have over here something hitting your electron hits the nitrogen and takes off that electron, and you can have a nitrogen that is a radical cation. That can then pull this over to make a double bond there, which is going to give you a benzyl radical. So here we have your 77 radical, and you have a cation, because when you make this double bond, you are going to have a nitrogen that is double bonded to a carbon that's double bonded to an oxygen. So double bonded to an oxygen and 2 hydrogens. And if you take the formal charge here, 1, 2, 3, 4, 5 minus 4 is a 1. So therefore, this is going to be a positive. And the mass of this is going to be 44 m/z. This is your 77 radical that's going to go out through your chute. If you recall, 77 here, this is a benzylic compound, and they have had, just like your tropylium cation spat out a alkyne, you can have this also do a similar thing. Pretty much, this is just kind of a suggestive pathway. You can take this out. There's 2 hydrogens. In fact, there's hydrogens in all of them except here. And so you can see how this can spit out an alkyne, which is going to be neutral. And it's going to give you a 4-membered ring. So I know it's crazy as it looks. That's what's suggested. C4H3 plus 48 and 3 is 51 m/z. 51 is over here. A very common fragmentation pattern involves alpha fragmentation, and you can see this happening over and over again. Here's right next to that group, cleavage here, and even with the hydrogen. So it's giving you 3 different peaks. Over here too, you can see this is your carbonyl. Right next to it, you're cleaving that. And on this side, you're cleaving this. And here is kind of a rearrangement here to give you a peak. Even though this kind of sounds crazy that you have actually a benzene breaking apart, that's what's suggested. Don't ask me about the stability of this molecule. Looks pretty bad. But these are things that only last like a nanosecond. So you can see them on the mass spec as these transient compounds just fly through. Just practice different compounds. Now that you've seen so many, just pull up stuff and just practice different functional groups. All right, guys, so if you have questions, See you soon.